In this video, we will take a brief look at the most common and important menu items in ElectroFlo. In subsequent training exercises, we'll re-examine these functionalities and discuss them in more detail. As I mentioned in part 1, ElectroFlo's main menu is displayed at the top of the page. Let's look at the selections in the File menu first. Of course, many of these are standard, so I won't spend time going through all menu picks. Recover. This uses the CMod extension. This keeps track of the model after each command. In case the computer crashes at a point, you can restore your model by opening the CMod file. The undo files basically invoke the same functionality. Session file. A session file can be used to quickly do a series of commands without using the graphical user interface. These files are modified after every command in the GUI, so they can be used to automate certain routines. Save backup. This will keep the model in the same location, but saves a backup of the database and history file to the specified location. Import database. This loads an existing ElectroFlo component or model into the current model. The model will be placed in the same global position and orientation as it was saved, so it may be necessary to be translated and or rotated. Import component placement file. This loads the electronic components from a component placement file into the current model. The file must be located in the components directory in the application folder. This file specifies the component's name, XYZ location, and its orientation. We will see how this works in great detail later. Geometry in ElectroFlo has a hierarchical structure. It starts with models, assemblies, parts, solids, blocks, surfaces, and points. Models. Each model is represented by a database. This database contains all of the geometry, boundary conditions, model parameters, and other aspects of the model. Multiple models can be opened, displayed, and run at the same time, but the user can modify only one model at a given time. The current model can be selected using Current Part button at the top right. Assemblies. Each model is comprised of assemblies. By default, an assembly named model will be created with the part named default that all solids will be added to. The user can create new assemblies. Parts. Assemblies have parts. Default is the name of the part that's created in the assembly name model. The user can create parts and assemblies using the Current Part button or from the list view. Geometry menu. Import geometry. This lets you import geometry using various formats for CAD, components, and traces. Please refer to our user manual for an in-depth discussion of various formats. We will use and demonstrate this functionality extensively in the upcoming exercises. Create geometry. This form allows the user to create new geometry in ElectroFlo. The form look changes based on the choice of solid type. Here the user specifies the location and material, either chooses from the list of materials in the library or types a new name for a user-defined material. Later, the material properties can be defined in Materials menu pick. The Give Priority button is very important. It must be set on when creating a solid that potentially overlaps with another solid. A good example is traces in the board or thermal vias. Modify geometry. We've already seen that you can open this form by clicking on any solid with the selection control on Objects Solid. This form can also be opened from the menu pick. Its purpose is mostly for modification of a single solid. For modifying multiple solids, it's best to use the List View Modify Solid form. All solids of the selected types are displayed in the list box. Using this form, you can change size, location, material, move and make multiple copies of any solid. I will skip the next three items as they are not used frequently. Nodes. Nodes or capacitance nodes are used to model things without actually creating the geometry for them. Nodes can be thermal, electrical, or both. As an example, nodes can be used to represent internal details of electronic components, such as components junction, or external solids that you do not want to model in detail, but you would like to take their effects into account. Element links are a way to provide thermal and/or electrical connection between elements and nodes without modeling the connection details. An example would be leads of components or wires. Links can be modeled using geometric option by providing material, length, and cross-sectional area, or user-defined by providing its thermal conductance or electrical resistance. We can see many links in this model, drawn using red or yellow lines. Red lines indicate thermal links and yellow lines indicate electrical links. Coordinate frames. Coordinate frames are used to have different frames of reference for different groups of geometry. For example, if you had a printed circuit board and components locations were given with respect to the board's coordinate frame, separate from the rest of the model. Here we have the ability to specify the origin and the direction relative to the global directions. Materials. The material properties are either user-defined or selected from the library. To reference a material from the library, the user must select from the materials provided in the list box. A user-defined material is created by typing the material name that is not contained in the library. The name is added to the materials name list for subsequent uses. In material form, the user can access any material used in the model from a combo list box. The material properties can be constant or temperature dependent. The thermal conductivity can be isotropic, meaning no directional dependence, or orthotropic, with different values in each direction. Materials can be electrical conductor or insulator. If the value of electrical resistivity is in the conductor's range, all solids using this material will be included in voltage calculations during electrical analysis. Any region in the model that is not occupied by a solid is assumed to be fluid, unless non-CFD solution mode is selected, in which case the fluid elements are not included. ElectroFlo assumes air to be the default fluid. If the user wants to use a different fluid, he can change the fluid using the fluid form. Boundary conditions. Once the geometry has been created, the appropriate boundary conditions should be associated to the geometry. Each boundary condition form is of a similar format, with a plane or region section where we define the application region, and the data section where we specify the value, which can be constant or varying based on any solver variable using any mathematical function. All boundary conditions operate in create or modify modes, and the form changes based on this choice. Some boundary conditions can be associated to different types of geometry, and some have extra values to be specified. For example, fan boundary condition has a region field that can be rectangular or circular, and based on your choice, the data requirement changes. The flow can be assigned using a fan curve or fixed value based on mass or volumetric. You can optionally provide the fan hub information. The fan swirl can be modeled with circular fans. There are two types of contact resistance boundary conditions available in ElectroFlo. The plane resistance boundary condition is the basic way to apply any contact resistance. Here you can choose thermal or electrical contact resistance and provide its value in the area resistance unit, meters squared C per watt for thermal and meters squared ohm for electrical. The solid resistance boundary condition allows you to set a resistance between one solid and either a group of solids or all solids in specified directions. You then specify what the interface material is and how thick this coating is. Wire connection gives the user an easy way to model any external cables and wires that are attached to the model. The user can select the cable type from a list, supply the current and the wire ambient temperature. You can also optionally include crimp heating in your analysis using a value for contact resistance. Mesh. Mesh creation is fundamentally tied to the definition of geometry and boundary conditions. Creating geometry and defining boundary conditions result in the automatic creation of key planes, which are formed along solid boundaries and boundary condition application regions. Note that the mesh global parameters include enough flexibility to automatically pack the mesh in the fluid near a solid fluid interface. Specify element spacing next to the solid fluid interface or key plane. Provide a maximum element size and a mesh grade, which determines how quickly elements change size away from a key plane. This provides the ability to automatically obtain a mesh with the desired qualities of being refined near solid boundaries and coarsened in regions where high gradients are not expected. Create mesh. This automatically generates the mesh. Edit mesh. Edit the mesh globally or locally by key plane section. Method 1 is based on size and grade, and methods 2 and 3 are based on the number of elements and a grade. Method 2 is one-way biased. The user provides the element size ratio of first to last, and method 3 is two-way biased, for which the user gives the ratio of first to center. Key plane edit. Since key planes are the foundation upon which eFlow mesh is constructed, ElectroFlo includes utilities to optimize key plane location and to create new ones. Model verification adjustment. Merge key planes in order to reduce the extremely small elements and to remove parts of the model that fall below a threshold for modeling. This adjustment can be made in X, Y, and Z directions. New key plane. Add key planes to extend the boundary of the model or to make sure that critical parts of the model will not be moved when merging key planes. Objects at key planes. This is a tool for finding which objects are associated to which key planes and merging these key planes if desired. Tools. A series of vital tools are aimed at reducing modeling time, error checking, and standardization. These tools not only help novice users, but can potentially save advanced users hours and in some cases days of modeling time. The Model Manager List View tool. We have already discussed briefly, and we will take a more in-depth look at this in the next session. Member Display. This is an error-checking tool to ensure all solids are modeled as intended. This tool provides a plane plot where objects are colored by their material or solid name. The user can sweep the field between key planes to make sure that all solids are modeled and not accidentally overwritten. Electric connection. This is only relevant when Include Electrical Effects option is checked in the model parameters. A pre-processing tool examines all elements and using element electrical resistivity and electrical links identifies individual conduction regions or circuits. The circuits are then displayed in different colors. Tools are available for the user to examine various circuits and check for continuity and proper amperage. You can also create a group of any number of circuits to examine or display results on. Group Assemblies Parts. This tool allows the user to modify the members of a group, assembly, or a part. The options include translate, rotate, mirror, scale, or delete. Preferences. Gives a few options to customize ElectroFlo. Applying changes will make the changes for the current session, while Save Global Parameters will affect the installed copy of ElectroFlo until the option is changed. Units. This is used to set the units that will be used for each type in the current model. The user can also define new units to be used in a model. This is done by providing a name for the unit and a conversion factor. Sensors or sensor points. These are used for monitoring the temperature at desired locations during the simulation. These are like thermocouples that the user can place anywhere in the fluid or inside of a component. Temperature values at the first 15 sensor points are displayed graphically as a bar chart during the ElectroFlo execution. Temperature values at all sensor points at each time level are reported and saved in the sensor file. There are many other tools available that are not necessarily used in every session. We will see more of these in more advanced exercises. Parameters. These allow the user to control various aspects of modeling and simulation. Model parameters. This is displayed during the initialization of a new model. It is also available at any time using this menu pick. From this form, the user selects unit of length, the solution type, whether it's a steady state or transient, the flow regime, laminar or turbulent, the initial temperature, the gravity field, and whether radiation and electrical effects should be included in the analysis, as well as tolerances for the creation of radiation surfaces and solids. Note that the locally defined temperatures will take precedence over initial temperatures specified here. Solution parameters. From here, the user selects the analysis type. Whether a full CFD solution will be performed by solving the conservation of mass, momentum, and energy, or only the conduction solution is required by solving the energy equation only. The frozen CFD option uses whatever flow field that has been calculated up to that point to complete the solution and stop solving the flow equations. This allows the user to get fast solutions for problems that are mainly conduction driven. The non-CFD option completely ignores fluid regions and performs conduction analysis on solid regions only. The fluid interaction can be taken into account through the use of convection boundary condition. Also, the split air and solid option allows the user to separate the fluid mesh from the solid mesh. This way, internal details within a solid, such as board traces, component dies, will not affect the quality of the CFD mesh. This mode of operation uses ElectroFlo's multi-system analysis capability. From this form, you can also restart a solution from a previous run by checking the Restart from Existing Solution box. And you can control how often the voltage field should be solved in electrical simulations by setting the number of iterations between solves or change in max temperature. Turbulence parameters. These allow the analyst to specify the type of turbulence model to be used. Solver parameters. These allow the user to enter solver parameters that fall into 4 categories: iteration controls, convergence controls, tolerance controls, and relaxation factors. Iteration controls are used to specify maximum number of passes the solver will perform in different parts of the solution process. Max flow must be equal or less than max overall. Max flow control indicates the number of outer iterations the solver will perform with full CFD capability. By adjusting the max flow iterations, the user can solve flow to a point, freeze the flow field, and then use this velocity field for the remaining iteration in the analysis. The convergence controls are used to specify the level of accuracy deemed acceptable by the user in solving the specific problem before arriving at the final or converged solution. ElectroFlo provides the user the ability to use different tolerances for flow and overall or thermal convergence. In many instances, it is not necessary to require the flow field to converge to the same level of accuracy as the thermal field. In these situations, the user can potentially save significant time by solving the flow variables to a reasonable limit and then use this information to proceed bypassing the CFD solution in the frozen CFD mode. Field solver tolerances are used to control the accuracy for the solution of temperature, velocity, and pressure fields. The default values have been tested in a number of models and shown to provide accuracy and performance. The relaxation factors are used to control the convergence rates. A higher relaxation factor can possibly arrive at the final solution in fewer iterations, but it can also lead to flow divergence. To get a better feel for a relaxation factor, it's helpful to think of them as time steps in transient analysis. ElectroFlo automatically adjusts the relaxation parameters for forced or natural convection conditions. However, the user can further adjust these values to accelerate convergence or to prevent divergence. The transient parameters. This menu is used to provide data related to a transient run. The user provides the analysis start and end times and proceeds with breaking the total analysis time into a number of sub-intervals as required, and providing the number of steps in each time intervals. And finally, the output parameters gives the user the ability to select solver variables to be included in a result file for post-processing by the GUI by enabling the available checkboxes. Analysis. Clicking Run creates a solver input file for the current model and starts the solver to run the analysis. Subsequently, the solver execution window will pop up to display relevant information during the simulation. Modify existing job menu pick is used to modify or stop a job that the solver is currently running. It lets you change the time step being used as well as change whether CFD mode is on, off, or frozen. It also lets you dump the current output of the job and exit after the next iteration. Multi-system setup is used for eFlow's multi-system analysis capability. This feature will be discussed in detail in an upcoming training exercise. Results. The successful completion of an analysis in ElectroFlo will result in the creation of a result file. At this stage, the user is ready to view the results or post-process. The result file will automatically be loaded after a successful run, or it can be read in at any time. A variety of methods are available in ElectroFlo GUI, which allow the user to gain a great deal of insight into the generated results. These methods include plane plot. This feature allows the user to obtain either a combination of fringe vector plot of a temperature and velocity, or a fringe plot of temperature, or any other variable on a specified plane. For the combination fringe velocity vector plot, the vectors are automatically colored according to the temperature and scaled according to velocity magnitude. The user can also set the scale for the velocity vectors to make it easy to examine the flow in low velocity regions. Draw critical temperature results. This feature provides the ability to assign critical warning normal temperature limits to selected solids. These solids will be colored red, yellow, green based on their calculated temperature. The values for the critical warning normal temperature are set in list view. Average temperature. ElectroFlo includes a utility to allow the user to easily obtain the average temperature on fluid and solid, fluid only, or solid only, over a specified range. Result Viewer. This automatically exports the simulation result into the external post-processing package ParaView for advanced post-processing. Planar Region Results. This utility allows the user to select a surface in the model to examine various thermal and flow results on it. Volumetric Region Results. This utility allows the user to select a volume in the model to examine various thermal and flow results in it. View. Colors. ElectroFlo assigns certain default colors for various entities. Temperature, for example, is shown with red color. Convection boundary condition is colored green. The user can choose to change these defaults. To change the default color, right-click on the color with your mouse. Color tablet will appear. Choose the color from the color tablet and click OK. Geometry colors. From here, the user can change the colors used for assemblies, materials, and parts. All solids in the model can be colored based on chosen default color assigned to material, assembly, or a group. The spectrum control. This provides the ability to set the number of colors and the spectrum type. Windows positioning. This is used to set the location and sizes of the graphics windows in the main ElectroFlo window. 3D view, shortcut F3. This maximizes the 3D window, leaving room on the right side for tabbed forms. eFlow default, shortcut Control E. This places the 3D and 2D windows equally sized, leaving room on the right side for the tabbed forms.